Hello, welcome back. So, in the last class, we started looking at KKT conditions for a constraint optimization problem. In particular, we consider this problem where we want to minimize f of x subject to the inequality constraints of the type hx less than or equal to 0. There are L such inequality constraints. So, we define the constraint set to be capital X like this, and for a given feasible point x star, we defined an active set A x star to be the set of all constraints which are satisfied with equality. So, set of all z's such that hx star is equal to 0, and then we have the necessary conditions for a local minimum. These are the first order conditions because they use the first order derivative information. So, if we take a feasible x star, then that feasible x star is a regular point and is also a local minimum, then there exists a unique vector lambda star such that these conditions hold. So, gradient f x star is written as a non-negative linear combinations of the gradients of the active inequality constraints, and for the inactive inequality constraints we can set lambda j star to be 0. So, in all we have all lambda j star non-negative and this condition holds. So, for the inactive inequality constraints hx star is less than 0. So, for those constraints lambda j star will be 0, and for the active inequality constraints lambda j star will be non-negative. So, we saw that x star lambda star is a KKT point where x star is a feasible point and lambda star is non-negative. So, such points we are going to call them as KKT points, and if we define the Lagrangian function to be f of x plus sigma lambda j j x, where j varies from 1 to L, then this condition can be written as the gradient of the Lagrangian with respect to x evaluated at x star and lambda star is 0, or evaluated at a KKT point is 0, and the multipliers lambda j's are called the Lagrangian multipliers and they are non-negative. Moreover, we have this complementary slackness condition which is mentioned here, that lambda j star hx star is equal to 0 and lambda j star is 0 for all constraints which are inactive at x star. So, all this analysis holds provided the active set is known, and typically in practice the active set is not known. So, one has to investigate all possible active sets for finding KKT points, and we saw one example in the last class that if you want to solve this problem, minimize x1 square plus x2 square subject to the constraint x2 less than or equal to 1 and x1 plus x2 greater than or equal to 1. So, we have x1, x2 and we have one constraint which is x1 plus x2 greater than or equal to 1 and the other constraint which is x2 less than or equal to 1. So, if we look at the feasible region, so this is the constraint which satisfies x2 equal to 1 and this is the constraint which satisfies x1 plus x2 equal to 1. So, our set X is the feasible region where x2 is less than or equal to 1 and x1 plus x2 greater than or equal to 1, and our aim is to minimize the objective function whose contours are like this. So, you will see that at this point the minimum occurs, and that point is but then we do not know the active constraint beforehand. So, we have to check all possibilities. So, if we assume that at this point the minimum occurs, then can we satisfy the KKT conditions, or only this constraint x2 equal to 1 is active and this constraint is inactive. That means the solution lies somewhere on this line. Then what happens? So, we saw that the solution cannot lie here, and we saw in the last class that the solution indeed lies here. We were able to get x1 x star to be half half and the corresponding lambda which is positive, such that these conditions, the KKT conditions, are satisfied. Now, I will leave it as an exercise to check whether the solution does lie on this line. So, in other words, we have to check all possible combinations of constraints and treat them as active sets and see which are the possible KKT points. So, we saw this example in the last class. Now, another important point that needs to be noted is that a KKT point, it can also be a local maximum. So, satisfying KKT conditions does not mean that we will always get a local minimum. So, let us consider one example where we want to minimize minus x square subject to the constant x less than or equal to 0. So, this is just a one dimensional optimization problem. So, we want to minimize minus x square subject to the constraint x less than or equal to 0. Now, if you write the Lagrangian, so Lagrangian of x lambda will be minus x square plus lambda x. So, the partial derivative of L with respect to x, and that is 0 at the first order KKT conditions. So, we will equate that to 0 to get a KKT point, and this implies that minus 2x plus lambda is equal to 0. Now, if you consider the case 1 where so we divide the constraint into two parts. So, at the solution, suppose this is active constraint. So, in other words, at x star the constraint is there is only one constraint here. So, suppose that constraint is active. So, therefore, x star is equal to 0, because at x star j x star equal to 0 is a active constraint. So, if we put x star equal to 0, what do we get? Therefore, gradient of L with respect to x evaluated at x star lambda star equal to 0 implies lambda star equal to 0, because x star is 0. So, therefore, 0 comma 0 is a KKT point, because our KKT necessary conditions just say that lambda star has to be non-negative, and so in this case it is 0 and the corresponding point x star is 0. Now, so let us see, so if you look at this function, So, if we take the function minus x square and the constant x less than or equal to 0. So, x less than or equal to 0 means we are interested in the non-positive values of x, and the function would be like this. So, you will see that the function is unbounded. So, the minimum of minus x square will not be attained because the function is unbounded. Now, let us look at the point x star equal to 0. So, which is this point which we were considering, and we were able to get a non-negative Lagrange multiplier corresponding to x star, and we got 0 0 as the KKT point, and you will see from this figure that in fact this point is a local maximum. Okay. So, although this point satisfies the KKT conditions, it is a local maximum. Now, so therefore, satisfying KKT conditions does not guarantee local minimum. Now, similarly, one can work out the other condition that at x star the constraint is inactive. That means that at x star lambda is less than 0, and then one can find out what happens to this condition as well as the condition that lambda star has to be non-negative. So, I will leave it as an exercise. Okay. Now, let us look at another important point that needs to be understood, and that is called the constraint qualification. Now, every local minimum that we get need not be a KKT point, and one example which was given by Kuhn and Tucker sometime back in 1951 was a problem where we want to minimize minus x1 subject to the constraint that x2 minus 1 minus x1 cube is less than or equal to 0 and x2 greater than or equal to 0. So, let us look at this example. So, suppose this point is 1 comma 0 and so this is one constraint and the other constraint is x2 greater than or equal to 0. And we want to minimize minus x1 subject to the constraint x2 minus 1 minus x1 cube less than or equal to 0 and x2 greater than or equal to 0. So, we will write it as minus x2 less than or equal to 0. So, this is our constraint set and we want to minimize minus x1. So, now let us look at this point. Now, at this point we will see that this point indeed is a solution to this problem, because we want to find out the maximum value of x1 where these constraints are satisfied and that turns out to be this value. But let us look at the gradients of the objective functions and the constraints. So, let x, so this is x star. So, x star is given here. Now, at x star, which is equal to this point. What is the gradient of f of x star? So, gradient of f of x star will be minus 1 0. Let us take the first constraint. So, gradient h 1 x star will be 0 comma 1, because we are evaluating it at 1 comma 0. So, the x component, the x1 component of this first gradient will be 0, and the gradient of the second component, the gradient of the second inequality constraint will be 0 comma minus 1. Now, let us plot these constraints on this figure. So, gradient f x star, so is pointing in this direction. So, this is gradient f x star, and gradient h 1 x star is pointing in this direction. So, gradient h 1 x star and gradient h 2 x star is pointing in this direction. Now, the first order Kaketti conditions say that gradient f x star is written as a non-negative linear combinations of the gradients of the active inequality constraints. Now, at this point x star, both the constraints are active. So, both the inequality constraints are active at this point x star, and you will see that gradient h 1 x star and gradient h 2 x star are not linearly independent in this two dimensional space, and therefore, since they are not two linearly independent vectors in two dimensional space, therefore, they cannot form a basis for a two dimensional space, and therefore, gradient f x star cannot be written as a non-negative linear combinations of gradient h 1 star, h 1 x star and gradient h 2 x star. In fact, you will see that the gradient f x star is orthogonal to gradient h 1 x star as well as gradient h 2 x star. So, even though x star is a optimal point of this problem, it is not a Kaketti point, and that is because x star is not a regular point. The gradients of the active inequality constraints are not linearly independent in this case, and therefore, Kaketti conditions are not satisfied at this point. So, it is very important to have the regularity assumption for getting the Kaketti points. And therefore, this linear independence constraint qualification is a very important constraint qualification condition, and that says that the gradients of the active constraints active at x star have to be linearly independent. So, that implies that x star becomes a regular point, and once it is a regular point, once we have these linearly independent vectors, we can write the gradient of f of x star as a non-negative linear combinations of the gradients of these points. If they are not linearly independent, we cannot write gradient f x star as a non-negative linear combinations of this. So, this is a very important condition that needs to be satisfied. Then we can say that under the linear independence constraint qualification, if x star is a local minimum, then first order Kaketti conditions are satisfied or they are necessary. Now, Mangasarian and Promowitz also gave another constraint qualification condition, and that says that if we consider the problem of minimizing f x subject to h x star less than or equal to 0, then there exists at least one direction which makes an obtuse angle with all the gradients of the active inequality constraint. So, gradient h x star transpose d is less than 0 for all j belonging to the set of active constraints at x star. So, there exists at least one direction which satisfies this. So, this is another constraint qualification condition that was proposed by Mangasarian and Fromowitz. Now, let us consider a problem to minimize f x subject to the constraint h x less than or equal to 0, but this time we make an assumption that f and h z are differentiable convex functions. Okay. So, the important point here is that both f as well as h z are convex functions and also they are differentiable. Now, under this situation, it turns out that the first order KKT conditions are sufficient if x star is a regular point. Now, we are optimizing or minimizing a convex function subject to the constraint that h x is less than or equal to 0. Now, as we have seen earlier that if h x is less than or equal to 0 and where h is a convex function, then the set x such that h x less than or equal to 0 is a convex set. Now, if we combine different convex sets or the intersect different convex sets, then we know that the intersection of convex sets is also a convex set. So, the constraint here is a convex set. The objective function to be minimized is a convex function. So, such a program is called a convex program, and clearly the set x is a convex set. Now, there are two important results that I would like to mention here related to a convex program, and the first result is that every local minimum of a convex program is a global minimum. We saw a variant of this result when we studied convex functions, that under the unconstrained case we saw this result, and those ideas can be extended to a constrained problem like this, which is a in this case is a convex program. So, every local minimum of a convex program is a global minimum. So, there is no question of local minima as far as convex programs are concerned. Every local minimum is a global minimum, and not only that, all these global minima, when they are found, they form a convex set. So, the set of all optimal solutions to a convex program is convex. So, this is a very important result again, that not only do we have the problem of local minima for convex programs, but the set of all solutions to a convex program is a convex set. So, this is a this result again we have seen earlier, that even if we take an unconstrained optimization problem where we want to minimize a convex function, then the set of all optimal solutions is a convex set, and that result can easily be extended to a constrained problem, constrained convex program, which is given here, that the set of all optimal solutions form a convex set. So, here we have a important result that says that if x star is a regular point, then for x star to be a global minimum of a convex program CP, the first order conditions, KKT conditions are necessary and sufficient. So, we have already seen that if x star is a local minimum, then first order conditions are necessary. Now, we will show that for convex programs, these conditions are sufficient, and to show that we will need the convexity of f and the function hs. So, let us see how to prove that. So, let us take a KKT point x star lambda star, and since it is a KKT point, x star belongs to the feasible region and lambda star is a non-negative vector. Now, what we want to show is that x star is a global minimum of a convex program, where f is a convex function and hj are convex functions, and we also assume that they are sufficiently smooth. Now, in this case we just need a first order derivative. So, it is enough to assume that they belong to class C1 of functions. Now, to prove that the KKT first order KKT conditions are sufficient, we will use the convexity of the functions f and hj, and for that purpose let us consider any point x in the feasible region. Now, we have seen this result earlier when we studied convex functions, that an affine approximation of a convex function at x star does not overestimate the function. So, f of x is always greater than or equal to f of x star plus gradient f x star transpose x minus x star. So, this result we have seen earlier. So, let us make use of this result to prove that a KKT point under the regularity assumption is a local minimum, is a sufficient condition for the local minimum of a convex programming problem. Now, since x is a feasible point, hjx is less than 0, and x star lambda star is a KKT point. So, lambda star has to be non-negative. So, this quantity here is a non-positive quantity, and therefore, we can write f of x to be greater than or equal to f of x plus sigma j lambda j star hjx, because hjx is less than or equal to 0 and lambda j star greater than or equal to 0. Now let us make use of this result. So, expand f x around f x star and use this inequality. So, f of x is greater than or equal to f x star plus gradient f x star transpose x minus x star, and since each hjx is also a convex function, hjx is greater than or equal to hjx star plus gradient hjx star transpose x minus x star. So, in this we have used the convexity of both f and h's. Now, let us rearrange these terms together. So, let us combine this term with this term, and then all the terms involving the gradients of f and gradient of hjx, we will combine them together. So, this gives us, so this quantity is nothing but f x star plus hjx star sigma lambda j star hjx star plus, let us combine the terms involving gradients. So, gradient f x star plus sigma lambda j star gradient hjx star transpose x minus x star. Now, we have seen that x star lambda star is, we have assumed that x star lambda star is the KKT point and satisfies the necessary KKT conditions. So, since the complementary slackness condition is satisfied, we have lambda j star hjx star to be 0. So, every term in this summation is 0. Now, let us look at this point. Since the first order KKT conditions are satisfied, gradient f x star plus sigma j lambda j star gradient hjx star is 0. So, this term is 0. So, this is 0, this is 0, and what we are left with is f of x star, and therefore, f of x is greater than or equal to f of x star for all feasible x, and that means that x star is a global minimum of the convex program. So, x star is a global minimum of the convex program that we have considered. So, if we find the KKT points of a convex programming problem, then under the regularity assumptions, those KKT points are indeed, or those KKT points give us the optimal solution x star to a given convex program. So, this is a very important result as far as convex programming problems are concerned. Now, interestingly, this result can be extended when we add the equality constraints to this program. The only thing that one has to keep in mind is that when we add the equality constraints, those equality constraints have to be of the type AI transpose X minus BI, because only then the constraint set will remain a convex set. So, we will see those results when we introduce the equality constraints to our optimization problem. So far we have been dealing only with the problems of this type where we want to minimize effects subject to the inequality constraints. But those results can easily be extended to a general convex programming problem. We will see those things sometime later. Now, let us again go back to our convex program, where the function f is a convex function and hjx are again convex functions, and the constraint set is a convex set. So, the feasible set X becomes a convex set because it is the intersection of all convex sets. Now, for convex programs, there is a constraint qualification condition proposed by Slater, and that condition says that there exists a feasible point y such that hjy is less than 0 for all the inequality constraints. So, what does this mean? This means that there exists some feasible point which lies in the interior of the feasible set X. So, that means that the interior of the feasible set is not empty. So, this latest constraint qualification is useful especially for convex programming problems, and it is easy to check that this condition to check whether this condition is satisfied or not. So, typically for convex programs we will use Slater's constraint qualification, and to show that to show the importance of this Slater's constraint qualification, let us consider an example. So, where we want to minimize this problem. So, suppose if we consider this problem, minimize x1 plus x2 subject to the constraint that x1 minus 1 square plus x2 square is less than or equal to 1, and x1 plus 1 square plus x2 square is less than or equal to 1. So, if we so, the first constraint is a circle of radius 1 centered around 1, 0. And the second constraint is again the so this is the points inside the second circle. These are the points inside the first circle. So, the feasible region will be only this point. Feasible set X is nothing but the origin. So, the dashed portion here just shows the points inside the circle. So, they form one set. So, this is the feasible region corresponding to the second constraint. This is the feasible region corresponding to the first constraint, and when we intersect, we get only one point, which is a singleton point. Now, this point, this feasible set being a singleton set has no interior. So, one can check that this point is a local minimum, but it does not satisfy the Slater's constraint qualification condition. So, this point which we have got, which is the origin, which is the feasible set, is a global minimum, but it is not a KKT point. So, one can check that this point is not a KKT point, although it is a global minimum, and that happened because we had a constraint set which was a singleton set in this case, and that did not satisfy Slater's constraint qualification. So, many times for convex programs, it is possible to have a minimum, but that minimum may not satisfy KKT conditions, and that is mainly because the Slater's constraint qualification is not satisfied. That is, there did not exist a point which lies in the interior of the feasible set, or in other words, the feasible set does not have interior, or it has empty interior. Okay. So far we have studied the problems of the type where we want to minimize fx subject to the constraint hx less than or equal to 0. Now, the ideas that we have studied so far cannot be directly used for equality constraint problem. So, now let us start looking at the equality constraint problems. Now, you will see that the constraints are of the type EIX equal to 0, I going from 1 to m. Now, there could be the EIX could be as simple as AI transpose x minus BI equal to 0, or it could be a different function, a nonlinear function of x. Now, can we arrive at some algebraic conditions for the local minima of this problem, and that is what we are going to study now. So, let us again assume that the objective function f and the EIs are smooth functions, and for the first order conditions we will require them to be continuously differentiable, and for the second order conditions we will require them to be twice continuously differentiable. So, here I just mentioned them as smooth functions. So, let us collect all possible x which satisfy EIX equal to 0. This should be EIX equal to 0. Now, let us consider a feasible point and then see what constraints are active at the feasible point. So, as per our definition, the set of constraints which are satisfied with equality. So, the set of all i's such that EIX equal to 0, and since x is a feasible point, so that means that EIX equal to 0 for all I. So, which means that all the equality constraints are active at any given feasible x. So, this set is nothing but all m equality constraints. Now, so we will look at the definition of a tangent of the feasible set at a given point x, and that definition helps us to characterize the feasible directions using algebraic conditions. So, a n-dimensional vector d is said to be a tangent of x at x, tangent of the feasible set at a given point x. Remember that x also is part of the feasible set here. So, if either d is equal to 0, or if we consider a sequence xk in the feasible set where none of the xk's is equal to x for all k, such that the sequence converges to x, and if we take the chord joining x and xk and then take the vector, the normalized vector xk minus x by norm of xk minus x, that converges to d by norm d. So, such a vector d is called a tangent vector. So, suppose we have a constraint. So, this is the constraint Ex equal to 0. Now, if we take a point x bar, now we take a sequence xk which is part of this feasible set. So, let us take the sequence of points which converges to this point. Now, if we take a chord joining each of these, so in the limit this chord will have this direction, and this is the tangent to this surface at x star. So, one can also have a tangent which is in this other direction by considering another sequence. So, this becomes a tangent set to this feasible region at x bar. Now, in 2-dimensional space, this tangent is a line. Now, in 3-dimensional space, it will be a tangent plane, and so on and so forth. So, we collect all feasible sequences in the region which converge to x bar, and then if we take a chord joining those xk and x bar and normalize them to a unit vector, then we get a tangent, and then find the limiting direction of those chords, that will give us the tangent to the feasible set at x bar. So, if we collect all the tangents of the feasible set x at a given feasible point x, and that is called the tangent set, and we are going to denote it by Tx. So, Tx denotes the set of all tangents of the feasible region at a given point x. Okay. Now, now let us see how to characterize this tangent set. If you recall, for the inequality constraints, we use the feasible set f of x, script f x, and then that script f x, the feasible set was characterized using f tilde. So, similarly, how do we characterize Tx? So, let us look at that part now. So, for that purpose, we will need the definition of a regular point. So, a point x bar in the feasible set is said to be a regular point if gradient E I x bar are linearly independent. So, this definition is similar to what we saw for inequality constraints. The only difference is that for the inequality constraints, we just had to take only those inequality constraints which were active, or for which Hj bar was 0, and then the gradients of those points have to be linearly independent. While here, since we are talking about the active equality constraints, all the constraints are active at any given point x bar, and therefore, point x bar in the feasible set is a regular point if the gradients of all active or all equality constraints are linearly independent, or gradient E I x bar I going from 1 to m is a linearly independent set. Now, we will use this result, we will not prove this result, but use this result that at a regular point x bar, the tangent set is characterized by the set of all directions D which are orthonormal to gradient E I x bar, or which are orthonormal to the gradients of the equality constraints. So, note that we are again using all i's going from 1 to m. That means that we are using all the active or all the equality constraints, since they are active at any given feasible x bar. So, the set of all these which are orthogonal to the gradients of the equality constraints at x bar. So, under the regularity assumption, one can show that T x bar is this set, and we will use this fact to derive conditions for the local minimum of a equality constraint problem. So, let us assume that x star, which is a feasible point, is also a regular point and is a local extremum. Now, note that we have mentioned here local extremum, so which means that it can be a local minimum or a local maximum. Now, let us consider any vector d which is in the tangent set T x. So, since it is a regular point, we have already seen that gradient E I x star transpose d equal to 0 for all I going from 1 to m. Now, let us consider any smooth curve on in the feasible set. Let us denote that curve by x t, where t is a parameter, is a real number, and x t denotes the some point x in the feasible region. So, all x t's are feasible. Moreover, at t equal to 0, we have x 0 equal to x star, and then the tangent at 0 we are going to denote by d. And there exists some positive a such that E x t equal to 0. So, that means that around or in the close interval minus a to a, if you take any t, then E of x t is 0. So, this is some set of feasible points in the neighborhood of x 0, and the points are parameterized by the parameter t. Now, we have assumed that x star is a regular point. So, that means that the tangent set at x star is characterized by the set of all directions which are orthogonal to the gradients of the equality, all the equality constraints. Now, x star is also given to be a local extremum of a given objective function subject to the constraints. So, that means that the derivative of f of x t with respect to t evaluated at t equal to 0, because x 0 is nothing but x star. So, this derivative is 0, and that means that gradient f x star transpose d is 0, or d is orthogonal to gradient f x star. Now, you will see that we have considered any d which was from the tangent set, and the tangent set is characterized by this under the regularity assumption, and if x star is a local minimum, then this holds. So, from this we will see that gradient f x star is orthogonal to gradient E x star for all i's, or in other words, gradient f x star is orthogonal to the tangent set T x star. So, if x star is a regular point with the constraints A I x equal to 0, where I going from 1 to m, and x star is a local extremum point, whether it is a minimum or maximum, it is a local extremum of f subject to these constraints, then gradient f x star is orthogonal to the set T x star. So, this is a very important observation, that under these conditions, the gradient of the objective function is orthogonal to the tangent set T x star, and tangent set T x star is nothing but the set of all directions which are orthogonal to gradient E I x star. So, we will use this observation to derive the optimality conditions for the local minimum of a equality constraint problem. Now, here is the important theorem which says that if x star, which is a feasible point, is also a regular point and is a local minimum, then there exists some mu star which is in m dimensional space, such that gradient f x star is a linear combination of gradient E I x star. Now, you would notice the difference between the necessary conditions that we obtained for inequality constraint problem and the necessary conditions for a equality constraint problem. So, the important difference is that the multipliers corresponding to this gradient E I x star are not constrained to be non-negative. So, mu I star, they just come from the space of m dimensional space. So, this m corresponds to the set of or the number of equality constraints. So, there is one multiplier associated with each equality constraint, and since all equality constraints are active, so there exist m multipliers corresponding to all the active equality constraints, and gradient f x star is written as a linear combination of gradient E I x star. Now, so what this means is that if we collect all active equality constraints, find out their gradients, then we can all, and if under the regularity assumption, we can always write gradient of x star to be a linear combination of gradient E I x star. So, let us look at the proof of this theorem. Now, let us combine all the constraints and write them in the form E 1 x to E m x as E x. So, let E x denote the set of all equality constraints. Now, x star is a local minimum. So, that means that the set of all these, such that gradient f x star transpose is less than 0 and gradient E x star transpose equal to 0, because this is a condition corresponding to the constraint and this is the condition corresponding to the objective function. So, we do not get a descent direction d which is feasible, and therefore, we can write it as this condition. Now, if we define two sets C 1 and C 2 to be all pairs y 1 y 2, Now, note that y2 is a vector here, where y1 is gradient f x star transpose d and y2 is gradient E x star transpose d, because E is a matrix. So, gradient E x star transpose d is a vector, and then take another set C2 where y1 is less than 0 and y2 is equal to 0. Then you will see that this is a convex set, C1 also is a convex set. So, C1 and C2 are convex set and they have a empty intersection. Okay. So, so if we have two non-empty convex sets which are disjoint, then we saw one result earlier which says that there exists a hyperplane which separates C1 and C2. So, we will make use of this result to get this condition, and we will see that in the next class. Thank you.